Hello everyone, I'm Justin Betts, a technical marketing engineer for NVIDIA Ethernet products and software. Welcome to our Introduction to DOCA for DPUs DLI course. We're so excited to have you with us here as we introduce you to the basics of DOCA and BlueField DPUs to help you begin your journey of using and developing for BlueField. This course is meant to be very introductory. BlueField DPUs and DOCA have use cases for both systems administrators and also developers. So with that, thanks again. And let's get started with our first module, Demystifying DOCA.
In its most broad description, NVIDIA DOCA is the set of software that includes libraries, drivers, runtimes, etc. that enables the consumption of DPU acceleration. The goal is to help enable rapid adoption of DPU acceleration features. Today, DOCA includes certified reference or example applications, APIs and programming frameworks, and solutions for accelerating and offloading network and data center infrastructure functions, such as storage. One of DOCA's primary objectives is to protect developer investment for these acceleration features as DPU hardware generations move forward. Changes to the underlying hardware and low-level drivers will not require developers to update their application. DOCA also enables a rich partner ecosystem of NVIDIA partners working on integrating BlueField DPUs and accelerated computing into their own products. And for those of us who are familiar with CUDA, it's similar in many ways to how we think about DOCA. CUDA is in many ways a platform to enable accelerated computing using GPUs. And similarly, DOCA is intended to be the platform or means of enabling our ecosystem, customers, and partners to leverage the different types of compute accelerators on BlueField DPUs. Now, with that high-level description of DOCA, let's start to explore its intended use. The ultimate strategy is to free up general-purpose x86 CPU cycles so that they can be more efficiently utilized for the compute applications performing the interesting work. Depending on the application and its I/O requirements, there can be a considerable amount of CPU time and effort spent on overhead. Things like getting data in and out of the application and around the system, or for common computing routines and tasks where a hardware implementation is far more optimized than the implementation for a general-purpose x86 processor. DOCA and DPUs are designed to provide a flexible platform to help pass or offload some of those tasks down into the ARM cores, or by using one of several dedicated hardware acceleration engines to handle the computationally difficult work involved with modern high-speed I/O solutions. Before we can really dive into thinking more about what DOCA actually is, let's take a few minutes to talk about the major IT personas that we have in mind for the design and consumption of DOCA. Since the BlueField DPU is ultimately a type of SmartNIC, it has an exceptionally wide set of use cases that cater to different personas and roles inside of an organization. We see two main pillars here: the developer persona and the admin persona. The way in which each of these personas uses DOCA will look quite different, as each persona has different goals and interacts with software in different ways. The developer persona is, as the name suggests, developers. These are the people that write code and have a hand in building and architecting applications. The second persona is the admin persona. These are typically network engineers and systems administrators or systems architects that interact closely with software, but do not write or build the applications that they're tasked with maintaining and deploying. This distinction between these two personas is critical to understanding the entire DOCA ecosystem and software stack. Unlike CUDA, targeted primarily to developers, DOCA has a wider audience as the DPU platform itself provides a wide range of capabilities, some of which do not require any application programming to be able to consume. Looking at the same information, but a little bit differently, by packaging. RUNTIME and SDK define the ways that you'll find the DOCA software bundled for distribution. As we'll see in some later modules, this is easy to install, but it's important that we highlight this distinction early so when we see RUNTIME, we'll think systems and network administrators, And when we see SDK, we'll think of developers and a developer experience. And for each of these personas, we package and consume DOCA a little differently. Starting with the things that we call DOCA RUNTIME, these are things like libraries and drivers that would need to be installed and provisioned in order to execute and run applications that leverage DOCA. The runtime also includes installation and configuration utilities and scripts to help change and manage functional settings on the DPU, and it also includes things like monitoring and telemetry agents, or DOCA services. Compare that to what we call the SDK, or Software Development Kit. When there's a reference to SDK, we'll want to think about the use and consumption for what that developer persona needs. Yes, all of the runtime components are also typically installed and used by the developer. But the SDK is intended to include libraries and drivers and APIs and tools that help developers write code and build their software intended to run on or with acceleration features on the BlueField DPUs. SDK Manager tends to be the easiest installation vehicle for these components to set up that environment, but the SDK can also be installed using package managers on your Linux distributions. We'll talk more about this in an upcoming module. So let's keep exploring DOCA in a little more detail. This picture helps illustrate the different DOCA components and how they're packaged. Again, similar to the previous slide, we're talking about packaging and how things are bundled for distribution. But instead of by persona, we're looking at what's installed in each of the two execution spaces, your host, and then also down on the BlueField itself. It's important to remember that DOCA applications and acceleration functions can be written for either consumption on either x86 or ARM architectures, and therefore DOCA applications can execute in either space, either on the host or on the BlueField itself. It's generally easiest to think about DOCA applications as running on the DPU, since it is the most obvious way to think about saving the x86 host CPU cycles, run the infrastructure and I/O tasks on the BlueField itself. That is in some ways the goal, but it isn't as simple as simply porting your x86 applications to run on ARM on the DPU. We'll discuss more of the subtleties of this in a later module. But if we start on the left of this stack, you'll notice the boundary between the x86 host and the BlueField system. Notice that with the BlueField, all of these components come packaged together in the BlueField BFB image. Everything that a developer or admin would need to either develop or deploy DOCA applications and DPUs comes pre-installed. That's both the SDK and runtime, and the utilities and services are all there. Above the BlueField in this illustration, the host packaging has a bit more to it. The main DOCA components, the DOCA SDK and the DOCA runtime, aren't bundled together. They can be installed individually with a more manual package manager process or by using SDK Manager. What's also notable about the host packaging is that NVIDIA offers a DOCA development container for x86 hosts that provides an emulated ARM environment with DOCA pre-installed to perform cross-compilation and for use in build pipelines. DOCA applications cannot be executed and tested in this container, and it is targeted for developers and build engineering. It does not emulate the full hardware environment of a BlueField DPU and is noted as build only in the diagram. Now if we pivot away from packaging and architecture models and zoom in on just DOCA, we've got a slightly different picture. This is an illustration of the more individual software components of DOCA and roughly how they're stacked together and depend on each other. The applications on top aren't actually software components. They describe the main pillars or use cases for DOCA and DPUs. But starting on the left with DOCA services, this defines the support of tools for provisioning, updating, and monitoring hundreds or thousands of DPUs across a data center. This includes DPU management tools, software-defined networking agents to control the networking policies and steering, and storage services, including emulated devices. DOCA services also include DOCA telemetry, which delivers real-time monitoring of the host with the power to collect, analyze, and reduce the data without any impact to the host CPU, and gather, among many other things, hardware-accelerated metrics. Orchestration enabled to deploy and manage the services running on the DPU, including the framework for service chaining, quality of service, and resource management. Then, as we look more closely at the DOCA libraries, you can see some things like DPI, or Deep Packet Inspection, is stacked on top of regex. DOCA provides a DPI library that leverages the regex runtime libraries. NVIDIA RiverMax offers a unique IP-based solution for any media and data streaming use case. RiverMax, together with an NVIDIA GPU, accelerated computing technologies, unlocks innovation for a wide range of applications in media and entertainment, broadcast, healthcare, smart cities, and more. Immediately below, the DOCA drivers represent the software components that, in part, DOCA libraries help abstract and future-proof, but they are also available to directly accelerate applications. For example, in the networking block of DOCA drivers, ASAP Squared is a runtime accelerator that accelerates Linux kernel TC, OVS kernel, and OVS DPDK data paths natively. When installing the DOCA BFB image, the default networking data plane out of the box uses OVS and OVS kernel, and any traffic through the DPU and into the user space OVS control plane on the BlueField is automatically accelerated into the embedded switch for line rate performance. Turning now towards some more examples of what DOCA is, let's take a quick look at what the DOCA DPI library provides. The DPI library provides a framework to easily identify patterns in the payload of network traffic. The DPI library combines several DPU accelerated features in addition to providing pre-processing or packet parsing functionality and post-processing routines so that the application developers can more rapidly write applications that take action based on the contents of network traffic beyond packet headers. Calling back to our conversation about personas, these DOCA libraries and APIs are targeted toward our developer persona. These libraries are written in and for C, the C programming language. Without the DOCA DPI library, application developers would have to write and maintain all of the code to parse packet headers and speak the low-level driver for the regex engine. Remember that part of the value of DOCA is to preserve investment for future hardware. So as underlying hardware and drivers change, applications that leverage DOCA will not require code updates or maintenance to support new hardware platforms and drivers and APIs. DOCA also provides a library for working with network flows that pass through the DPU. This is called the DOCA Flow Library. Again, for the developer persona, this library helps developers rapidly develop applications that depend on matching and handling network flows. The DOCA Flow Library provides a framework for building pipes that are a set of match and action criteria, and the ability to assemble these pipes into a complete network packet processing pipeline. Actions that can be taken on flows include modifying packet fields, encapsulating or decapsulating from a tunnel, counting, mirroring or copying, and policing or rate limiting. Use cases for this API are things like a network load balancer or NAT device, a network sensor, or for directing traffic for applications like service chaining. An example of the DOCA Flow library that we include as a reference application with the DOCA SDK is a DNS filtering application. This application provides an example of how to build DOCA flow pipes that match different traffic by their transport protocol and port numbers, and then forward them to different destinations. UDP DNS requests are matched and forwarded to the ARM for further DNS processing, while all other non-UDP DNS and TCP traffic is hairpinned out and onto the wire without modification or any action. Continuing along with some examples, let's take a look at what a DOCA runtime example for the admin persona looks like. The initial release of DOCA contains a sample application for transparent east-west IPSec encryption that's all offloaded and accelerated by the DPU. By running an open-source IPSec control plane for ARM, such as StrongSwan, this sample application takes advantage of runtime libraries and acceleration features. By running the IPSec control plane on the ARM cores, this is an example of an effective offload. Now, the x86 host doesn't have to spend any CPU cycles on that infrastructure function. It also makes use of the onboard encryption and decryption hardware accelerators to be able to achieve line rate IPSec without using either of the general purpose processors. The end result is that process and workloads on the x86 host have no awareness that this DOCA infrastructure offload is functioning underneath. An administrator persona can design and architect offloads and acceleration features using DOCA without having to develop or write code and custom software using DOCA APIs, making it more accessible to everyone. Zooming in a bit more on DOCA services, this includes some curated containerized applications that leverage DOCA acceleration. DOCA services are targeted for consumption primarily by the DOCA admin persona, the network and systems administrator. DOCA services are meant to be prepackaged or curated that make use of DOCA accelerations such as Firefly, time as a service, a distributed and accurate time sync for telco and 5G and other media applications. Another example of a DOCA service would be our DOCA host-based networking service. It is intended to provide an isolated environment for networking functions to be able to easily extend Layer 3 network fabrics with top-of-rack functionality built into the bare metal host provided by the DPU. This allows for the most scalable network infrastructure architectures. Host-based networking brings together a data center switch-like network infrastructure software stack, including FRR, free-range routing, to handle BGP and EVPN-powered VXLAN control plane, with a custom driver to translate the Linux kernel networking model into DOCA-accelerated high-speed networking performance. Now that we've seen a few tangible examples of what DOCA is, and what it is in the context of personas, let's introduce some ways to think about how to apply these types of accelerations and offloads. It may seem difficult at first to understand how to incorporate DOCA and DPU acceleration, offload, and isolation features to a data center architecture, but once you start to see more about what these opportunities look like, you'll notice that the applications are nearly endless. We'll spend some more time on these applications and use cases in a later module, but with DOCA freshly demystified, let's look at a real-world application and how it can be used. A wonderful example of applying DOCA and DPU acceleration is for bare metal cloud providers. If we look at the infrastructure functions that are the main pillar of their services, we'll see how DPUs can offload many of those functions, providing more x86 compute power to their customers, as well as providing things like security policy enforcement and storage offloads. Software-defined networking typically follows a client-server architecture, with some type of agent running on the node to receive configuration and updates and changes from a central controller. When shifting network infrastructure functions to the DPU, SDN functions and processing can also shift to the DPU. Storage offloads allow for virtualized storage flexibility and still deliver local storage performance. Data protection can be offloaded at any stage, in transit with network functions, and at rest with industry-standard encryption methods. DOCA and DPUs can also provide a means for a robust zero-trust security model. Administrative isolation boundaries between the DPU and the host allow for complete control for monitoring and enforcing security measures in a highly distributed and scalable fashion. Reduce and remove the dependencies and bottlenecks of dedicated security devices and appliances and push these functions into the DPU itself reducing complexity in the network infrastructure and fabric. Without a DPU, like on the left example, illustrates how the server itself shares its processing power with both the application workloads and also all of the infrastructure functions that may be in use, such as security functions, SDN agents, and the overhead of remote storage solutions. With DPUs and DOCA, it becomes possible to offload those functions onto the DPU ARM cores and look-aside accelerators, while simultaneously providing an isolated and secure administrative boundary between the customer and the internal IT infrastructure operations. This concludes our first module. In review, we covered a brief overview of DOCA, what it is, what it's used for, and the personas that interact with it. We also discussed some details about the DOCA software stack and what it all includes and brings to BlueField DPUs to provide developers and administrators with a flexible platform. Lastly, we looked at a tangible example of bare metal providers and how you can look at their infrastructure functions as candidates to be offloaded by the DPU to help you with your own projects and software architectures. We'll see you soon in our next module.